Good afternoon. I'm Norman Wildberger here at the University of New South Wales. And today we're going to talk about our fourth lecture, Infinity in Greek Mathematics. We're following John Stilwell's textbook, Mathematics and Its History. So this is a rather interesting chapter today because we meet two of the greatest mathematicians of the ancient age, Eudoxus and Archimedes. And we also discuss the ancient Greeks' attitude towards infinity, which was quite a different attitude than we have today. The trajectory of mathematics is rather interesting. I would say that there's the trajectory of mathematics, around the year 1900, the trajectory went off in a rather different direction. So there was kind of a trajectory, and then suddenly it went in a rather different direction. Something changed around the year 1900, and the 20th century would be, a lot of the developments would have been viewed very suspiciously by ancient mathematicians and former mathematicians. So ideas of infinity and infinite processes were adopted after the 1900s that were not at all accepted before that time. So the ancient Greeks had quite a different approach than we do today, and it's a little bit challenging for us to go back and try to imagine how they thought about things. But it's also very useful for us to do that as an intellectual exercise and to enlarge our own ways of thinking. So to the ancient Greeks, infinity was problematic. It was almost like a religious or philosophical notion, and its role in mathematics was unclear. So infinity to the ancient Greeks was something that one should think of in quotes. So for example, they thought about the sequence of natural numbers as something that went on in that direction and kept on going beyond one's view. One could go along with it for as long as one had patience and energy, but ultimately the sequence left you behind. Okay. So this kind of sequence, even though it was unending, but could not be encompassed. It did not make sense to say, let's look at all of the natural numbers at once. That was not something that the Greeks did, that they avoided saying that. These days, we don't have such scruples. These days, we just wave our hands and we write things like n equals the set 1, 2, 3, ... and we expect that this ... somehow encompasses all those numbers. So these days, we think this is an acceptable thing, but for most classical mathematicians, not just Greek mathematicians, but also Euler, Newton, Gauss, all the great mathematicians, they would have looked at this with deep suspicion. They would not have accepted this. So when we go back to the ancient Greeks, we learn a sort of a different way of thinking than the usual one today. All right, so our story today concerns primarily these two great mathematicians, Eudoxus and Archimedes. And probably there's no better way of introducing the subject than to read something from Archimedes. So this is a book. It's called The Work of Archimedes. And it's a compilation of his various books. He wrote on a number of topics. And it's compiled by Thomas Heath, the same fellow who edited those volumes of Euclid that I read from you earlier. Okay. It's also a very beautiful book. It's got lots of interesting commentary. And there's chapters Archimedes writes on the sphere and cylinder. That's one of his books. Another one is Measurement of the Circle. Another one on conoids and spheroids. On spirals, one of his famous books. On the equilibrium of planes. The Sand Reckoner, Quadrature of the Parabola. On floating bodies. The cattle problem is here as well. Okay. So those are some of the topics that he thought about. And here is the beginning of the book on the sphere and cylinder. It's a start of where Archimedes greets a fellow mathematician. Perhaps he was writing to someone whose name was Dositheus. Okay. So here is Archimedes introducing this present work. On a former occasion, I sent you the investigations which I had up to that time completed, including the proofs, showing that any segment bounded by a straight line and a section of a right-angled cone, which is to him a parabola, is 4/3 of the triangle which has the same base with the segment and equal height. Since then, certain theorems not hitherto demonstrated have occurred to me, and I have worked out the proofs of them. They are these. First, that the surface of any sphere is 4 times its greatest circle. Next, that the surface of any segment of a sphere is equal to a circle whose radius is equal to the straight line drawn from the vertex of the segment to the circumference of the circle, which is the base of the segment. I'll explain that later. And further, that any cylinder having its base equal to the greatest circle of those in the sphere, and height equal to the diameter of the sphere, is itself half as large again as the sphere, and its surface also, including its base, half as large again as the surface of the sphere. Now these properties were all along naturally inherent in the figures referred to, but remained unknown to those who were before my time engaged in the study of geometry. Having, however, now discovered that the properties are true of these figures, I cannot feel any hesitation in setting them side by side, both with my former investigations and with those of the theorems of Eudoxus on solids which are held to be most irrefragably established. Namely, that any pyramid is 1/3 part of the prism, which has the same base with the pyramid and equal height. And that any cone is 1/3 part of the cylinder, which has the same base with the cone and equal height. For though these properties also were naturally inherent in the figures all along, yet they were in fact unknown to all the many able geometers who lived before Eudoxus, and had not been observed by anyone. Now, however, it will be open to those who possess the requisite ability to examine these discoveries of mine. They ought to have been published while Conan was still alive, for I should conceive that he would best have been able to grasp them and to pronounce upon them the appropriate verdict. But as I judge it well to communicate them to those who are conversant with mathematics, I send them to you with the proofs written out, which it will be open to mathematicians to examine. Farewell. So that's Archimedes speaking to us, about 250 years before Christ. So let us talk about what he's talking about. There's a lot of content in those paragraphs, and a lot of it is, some of it will perhaps be unfamiliar to you, but interesting. So first of all, he refers to some facts established by Eudoxus. Let's start by a familiar formula that was known long before, that if you have a triangle and its base is, say, B, and its height is, say, H, then the area equals the base times the height divided by 2. Okay. That's a very familiar formula. And Eudoxus was interested in generalizing this to a 3-dimensional situation where we have, say, a pyramid with some kind of rectangular or square base, perhaps, and a vertex at a certain height above the base. So let's call the height h again, and let's say the base is that square there. And so Eudoxus' formula is that the volume of this pyramid is the base area times the height divided by 3. And one way of perhaps remembering this, or maybe even deriving it, is to think about a cube. Okay? If you think about a cube which has 6 sides and its center point, then that center point together with any one of its bases determines a pyramid just like we are talking about. So if the side of the cube has, say, side 1, then the total volume of the cube is, of course, 1. And then that will be equal to 6 times the volume of each little pyramid. Because there are 6 equal pyramids making up that cube. And from that we can immediately deduce that the volume of the little pyramid is equal to 1/6, which is indeed the area of the base times the height divided by 3, because in this case the height would be 1/2. Now, Eudoxus sort of realized that once you knew it for a pyramid, you could extend this to a more general result. So this also applies to cones. So if we have a base circle with a certain height, that's the base, let's say it has radius r, then the area of the base is pi r squared, famous formula for the circle. And if the height is h, then the volume is pi r squared h divided by 3. And the kinds of arguments that Eudoxus was familiar with and used would have allowed him to go from one of these results to another, because he thought about dividing such a volume into lots of little pieces and then adding up the cumulative little volumes. So one formula follows from the other by a suitable approximation argument. Namely, you could take the area of the circle, okay, and you could think of dividing that area up into a lot of little squares. And then with the other point of the cone, together you get a lot of little pyramids. And so the volume of the cone is going to be the volume of all those little pyramids, plus a little bit of extra stuff that's curved. But if the squares are small, then that extra stuff is relatively negligible. And so you can reduce or sort of go from one to another by thinking about decomposing your circle into lots of little squares. All right, so what are the results that Archimedes is discussing here? So he mentions a couple of different theorems. So the first has to do with a parabola. So there's a parabola. And remember, to the ancient Greeks, a parabola was something that you got by slicing a cone in a certain fashion. It wasn't necessarily y equals x squared, the way we think about it. So there's a parabola, and okay, what does he say? That any segment bounded by a straight line and a section of a right-angled cone is 4/3 of the triangle which has the same base with the segment and equal height. So it means that if we're, say, interested in that portion of the parabola, in other words, the area of that parabolic segment, then what you can do is you can look at a triangle with the same height. So if we draw kind of a parallel line through here and look at that point there, then this triangle will have equal height to the segment. That's what he's talking about. And his theorem is the relation between the area of the triangle and the area of the parabolic arc. And he's saying that theorem, that the area of the parabolic arc equals 4/3 the area of the triangle. That particular triangle that has its maximum height possible in the parabolic arc. Okay, so problem number 9 is to prove this in the special case when we're talking about the curve y equals x squared. And our triangle has one vertex at 0, 0. So this is some other general vertex. And so this is some point x squared on the triangle. So this is point 0, 0. Prove this in the special case when y equals x squared and one point is at the origin. Okay, so you all know a little bit of calculus. You know how to compute the area under a parabola. So you should be able to calculate the area of that parabolic arc segment, which is right there, and compare it to the area of the appropriate triangle. And the starred problem, problem 9 star, so this is for the Math 3560 students instead of this one. Same thing, but with any 2 points on the parabola y equals x squared. So if you have a point x1 and another point x2, prove it's true for general x1 and x2, not just with x1 equals 0. All right, so I've told you before that I think that Archimedes is the greatest mathematician of all time, and he was certainly a remarkable person. He lived most of his life in Syracuse, in Sicily, but he also studied in Alexandria. So Archimedes, he studied in Alexandria. He under the students of Euclid. So he was a few generations after Euclid, and Eudoxus was before Euclid, so he would have learned from Eudoxus and from Euclid. And most of the time he spent in Syracuse. And that was an independent island at the time, and there were wars going on between Rome and Carthage. They're called the Punic Wars. And so Syracuse got involved in that, not entirely favorably. And eventually the Romans laid siege to Syracuse, and eventually they captured it, and Archimedes died at the hand of a Roman soldier. Died when he was at age 75. Story is he was drawing some figures in the sand or something, and the Roman soldier came in into his compound, and he told the Roman soldier, don't mess with my circles or something. And the Roman soldier killed him. That was expressly against the laws of the rule of the general. The general was named Marcellus, I think. Marcellus, famous Roman general, and he laid explicit instructions that Archimedes was not to be harmed, because Archimedes already had a reputation of being this great mind, and everybody knew about him, obviously. So the Roman general did not want this to happen. But nevertheless, after he died, evidently the Roman general went into his office and took out this great planetarium model that Archimedes had made. Archimedes was a great astronomer too, and studied astronomy. One of his favorite things was a model of the universe at the time, with the planets and the moon, and that he had a mechanical model that kind of mimicked what was going on in the night sky. He made that. He was a great engineer. He was an engineer, a physicist, a practical person. So he helped the ruler of Syracuse in a number of battles against the Romans. He was supposed to have devised catapults, other machines of war. Some legend has it that he was able to focus the sun's rays using parabolic mirrors to burn some of the Roman ships. That seems highly disputable, whether that's possible, but so the story goes. He invented a screw that raised water in the Nile Delta to get water from one level to another. He discovered the important principle of hydrostatics, that if you have some water and you have an object in the water, some kind of blob, okay, that the water puts upward pressure on that blob. Okay, so this basic hydrostatic principle, that the upward pressure of the water on a submerged solid equals the weight of the water displaced. By that object. So for example, if there's a log at the bottom of your pool, and you dive down and try to pick up your log, you will find that the log is easier to lift up than it is out on the land. Now, how much lighter is it? It's lighter by exactly the amount of weight of the water that log displaces. Okay, so if you took that log and sort of emptied it out and filled it with water and weighed how much that watered log would be, that's how much the weight is reduced by. Okay. So this is the basic principle that allows a ship to float. If you have a ship, it's of course submerged, part of it's submerged, and the amount that's submerged has a certain volume. And so the force of the water up, keeping the ship up, is exactly equal to the weight of the water displaced by the hull. So if you know the shape of the hull, you can figure out where the water level is going to be, because then the force of gravity and the force of the water up exactly balance, and the ship is stationary. Archimedes applied his mechanical genius to his mathematics. And this was not well known until about 100 years ago. So people knew about most of Archimedes' writings, but some of them have been lost. But most of them come to us from Arabic translations. All right, so we don't have a lot of them in the original Greek. We have Latin translations of Arabic translations from the Greek. Okay, that's how we get Archimedes. And one of the notable things that people thought about Archimedes is his writing is kind of perfect. It's really like a beautiful thing. It's well crafted. There was a feeling that Archimedes sort of hid his thinking. But in 1906, a new document was discovered. It was a book called The Method. And in it, Archimedes reveals some of his secrets or some of his ideas for obtaining theorems. And it turns out that he had a very mechanical idea towards a lot of mathematical arguments. So for example, with the parabolic arc, okay, so another kind of thing that he knew is that if you have the axis there and you have a tangent like this, and you have another line parallel to the axis, that this thing here, this area of the parabolic arc and this area of the triangle are related. The area of the triangle is 3 times the area of the, that's supposed to be a parabolic arc. Okay, so that area of the triangle. Okay. So the way he discovered something like this was he thought in terms of lots of little line segments. You know, he thought of a little line segment. He thought of this parabolic arc as actually being physically made out of a lot of little pieces. And he thought about balancing things. The actual argument we won't go into, but he sort of had a way of figuring out where the center of mass of the triangle was and where the center of mass of this thing was and where they would sort of balance. Because he knew the basic principle, the principle of the lever. Well, probably this was known before, but he made it very explicit. And it's usually associated with his name now. The principle is that if you have a lever and you have a mass or a weight on this side, let's say weight W1 and another weight W2, let's make them balance. So this is shorter and this is bigger, bigger. Okay. No, that's the wrong way around. Right, that's not going to balance, is it? No. This is longer, so we can put a shorter mass here, well, make it a little smaller. It's W2. Can you believe that will balance? Okay, that's bigger there. That's smaller, but this one's further away. And the basic principle is that if this distance here is D1 from here to here, and this distance is D2 from here to here, that balance occurs precisely when D1 times W1 equals D2 times W2. So if D2 is, say, 3 times as long as D1, then this can be 3 times as heavy as that, and they will still balance. Okay? And there's a famous quote attributed to Archimedes that's something like, if you give me a place to stand, I will be able to move the world. And a lever long enough, I will be able to move the world. There's also a story of him, I think, having to do with some ships. There's some ship that had to be dragged onto the land or something for some reason, and they didn't know how to do it, but he was able to set up a pulley system because he sort of knew how forces worked. So he set up a pulley system and was able to utilize pulleys to drag this very heavy weight up on shore. So he's a very practical genius, but he also contributed to pure mathematics. This parabola result is really integration, right? You don't know how to do this in high school until you know how to integrate. It's basically an integration problem. And so Archimedes really was involved in the integral calculus. The integral calculus has its origins with Eudoxus and Archimedes. In history of mathematics courses, it's a favorite topic about who discovered calculus. Was it Newton or was it Leibniz? It's a favorite discussion, okay? And the English mathematicians all say, oh, it was Newton. And the German mathematicians all say it was Leibniz. Okay? But in fact, neither of them discovered calculus. Calculus had been around for centuries before them. First of all, Fermat made important contributions, a Frenchman. But long before Fermat, Eudoxus and Archimedes already had many of the ideas of integral calculus under their belt. They could do calculations. They could do calculus calculations by not exactly the same way we do. They didn't have the fundamental theorem of calculus, but the basic idea of splitting something up into lots of little pieces, letting the little pieces get smaller and smaller, and seeing what happens as the number of pieces gets big. So some evidence for that. So one idea that Archimedes had was to try to understand pi. Okay, so pi, very important irrational number. Okay, it's around 3.1415926. I can't remember how it goes. Okay, it's an irrational number. And what is it? Well, you can think of it either in terms of areas or in terms of lengths. So one way of thinking about it is the area of a circle of radius 1. Okay, so let's say this is a circle of radius 1. You can draw that circle and then you can try to calculate its area. Yeah, but how do you calculate its area? Well, Archimedes said, all right, well, what we can do is we can approximate it with a polygon. For example, we could take maybe a 6-sided hexagon. We could compute its area, which is not too hard. And maybe we could take another hexagon, which is outside the circle, which circumscribes it, maybe also a hexagon. Okay, so there's a sort of an inscribed hexagon and a circumscribed hexagon. And we can compute the areas of both of those. And then whatever pi is, it's got to be somewhere in between those two numbers. So it gives us a range of possible values. And then if we want to get something better than that, well, instead of using a hexagon, we should use something with more sides. We could divide the hexagon, for example, into to make it a 12-gon. Because he knew that if you took, say, if we just look at this triangle here, if you took this side here and you replaced it by a midpoint like this, okay, so you go from the equilateral triangle to one more like this, you have to add a little bit, but he could calculate how much you had to add. So you could do it for a 6-gon, and then a 12-gon, and then keep dividing by 2, 24-gon, 48-gon, 96-gon. I think he did it up to a 96-gon. He calculated the area of a 96-gon inscribed and circumscribed around a circle. Got two values and said pi's got to be in there somewhere. Okay. And that was the most accurate valuation of pi in the ancient world. Although the Arabs went further later on. But. So that's one, certainly a calculus kind of idea, that we want to get an area, so we divide it up into little pieces that we know, and we look at kind of a limit these days as the number of pieces gets bigger. All right, now let's return to what else he says in here. There's very interesting additional facts. So he says, since then, certain theorems not hitherto demonstrated have occurred to me, and I have worked out the proofs. They are these. First, that the surface of any sphere is 4 times its greatest circle. So it's a formula for the surface area of a sphere. Okay, well, let's take the sphere of radius little r. The greatest circle in it, by that he means an equatorial circle. Okay, so that circle there has area pi r squared. And his statement is that the surface area of the sphere is exactly 4 times the area of that circle. So it's 4 pi r squared. That's a rather sophisticated calculation. Most first-year students, even who have taken calculus for several years, I doubt if they could make that calculation. Unless you've been sort of told an explicit way of doing it, but it's a bit tricky. Okay, but he has more beautiful things. What else does he say? He also talks about segments of a sphere. So and he compares a sphere to a cylinder. This is so beautiful that I need to have some more room. Okay, so I'm just interpreting the words that I told you at the beginning of the lecture. So if you have a sphere, and let's suppose it has radius r as before. So its area of the sphere, well, let me write A. Area of the sphere is 4 pi r squared. Then you may know that the volume of the sphere is 4/3 pi r cubed. So Archimedes knew that. So he knows the area and he knows the volume. And he also compares it to a cylinder with the same cross-sectional circle and the same height. So there's a cylinder, also with radius r, and well, then its height is going to be 2r. All right, what is the volume of the cylinder? The volume of the cylinder is just the cross-sectional area times the height. So it'll be pi r squared times 2r. So that is 2 pi r cubed. And what Archimedes says there is that the volume of this sphere is 2/3 the volume of the cylinder. Same width, same height. The cylinder is obviously bigger because the sphere can sit inside it. But the volume of the sphere equals 2/3 the volume of the cylinder. What about the area of the cylinder? Well, the cylinder, and he talks about this, he says the closed cylinder. Let's look at the closed cylinder. So it actually has a closed surface just like this one. Well, it's going to have a side. The side is going to be the area of the side, which is going to be the circumference of this circle times the height. So that's 2 pi r times 2r. That's the circumference times the height. And then we have the top and bottom, and the top and bottom are both a pi r squared. So that's, well, 2 pi r squared for a total of 4 pi r squared here plus 2 pi r squared. That's 6 pi r squared. And how does that compare with the area of the sphere? Well, again, the area of the sphere is 2/3 the area of the cylinder. So he knew this, but he also knew that the area of the sphere equals 2/3 the area of the cylinder. It's beautiful. It's something that everybody should know. Archimedes realized this was beautiful, and so probably of all his results, he asked that on his tombstone, this result be commemorated. So on his tombstone, there was a picture of a cylinder and a sphere inside it, and some words having to do with the 2/3 ratios here. We know that because the Roman writer Cicero, politician, writer, some centuries later was assigned to go to Sicily and be an official there. And during his time in Sicily, he looked for Archimedes' tomb, and he found Archimedes' tomb, and it had fallen into disarray. And so he restored the tomb, and he wrote some remarks that he had observed this picture on Archimedes' tomb. But it's been lost today. I think no idea what happened to it. But okay, there's one more beautiful thing that Archimedes also mentions in that first paragraph, which is in addition to this. Okay, in addition, there's a remarkable fact that if you slice both the sphere and the cylinder with parallel planes, perpendicular to the axis, then they cut off equal area pieces. What I mean by that is, when we have the sphere and the cylinder sitting next to each other, we're going to slice with a plane perpendicular to this axis here, and then another plane parallel to that. And then that's going to slice on the cylinder. We're going to get a little a wedge. A cylindrical little slice of the cylinder, a little cylinder. And over on the sphere, we're also going to get kind of a spherical little cylinder. It's going to have curved sides. Okay. So these two pieces are, they have the same height because they're created from the same parallel planes. While the sides of the cylinder are straight up and down, the sides of this little spherical strip are curved. But they have the same area. Have the same area. Another way of saying that is that if you take an egg slicer, I'm not even sure if I've seen these in Australia, but I know in Canada that we have these egg slicers where you put an egg in, you want it to slice into little pieces, and then you sort of pull this little thing down, these little wires come down and just slice the egg. Do we have these things around here? Yeah. Yeah, okay. So you've got your sphere or your egg, and then you've got, it's like a lot of little parallel knives coming down, slicing it into lots of equal diameter, equal separated pieces. Okay? So what Archimedes is saying is that all of these pieces, even though they look quite different, they all have the same surface area. Right? Because the surface area only depends on the separation, because over here the surface area only depends on the separation. But over here it's obvious that this cylindrical strip is going to be the same as the one further down. That means that this cylindrical strip is over here corresponds to two spherical strips that are going to have the same area if the parallel planes are separated by the same amount. So although these strips, they all look quite different, they all have the same area, same surface area. Okay, so I can't see how anybody can look at this and realize that Archimedes knew this and not attribute knowledge of calculus to him. This is an exercise in second year advanced calculus. Well, it's not an exercise, it's something that you can do. After you've studied advanced calculus, second year calculus, you can make this computation if you're good. It's like a final exam question. In fact, it's probably one of the highlights of a second year advanced calculus course, known by Archimedes. There's another famous formula that Archimedes knew, which is now called Heron's formula. But it's really due to Archimedes. Heron was a mathematician who lived several hundred years later, but Arab sources clearly indicate that there were lost manuscripts in which Archimedes knew Heron's formula. What is Heron's formula? It's something that all school children used to learn back when they learned some geometry. Those days are sadly gone for some strange reason. But here's a triangle just in the plane, and it has sides D1, D2, and D3. These are the lengths. And the formula is that area equals square root of S times S minus D1 times S minus D2 times S minus D3, where S is D1 plus D2 plus D3 all over 2. That's sometimes called the semi-perimeter. It's 1/2 of the way around. So it's a formula for the area of a triangle in terms of the 3 lengths of the sides. Unfortunately, it's not really the best formula. There is a much better formula, which I would like to officially call Archimedes' theorem. I'm not sure if Archimedes knew this, but if we wrote it down, he would certainly look at it for a minute or two and say, yes, I know that. So what is Archimedes' theorem? So this is using the language of rational trigonometry. Which is a much better modern way of thinking about trigonometry. Okay, what do we do in rational trigonometry? Well, we go back to the ancient Greeks. And we realize that the ancient Greeks, instead of thinking about distances, they rather thought about areas of squares. So let's call the area of the square Q1, the area of the square here Q2, and the area of the square here Q3. Okay, so the quadrants is Q1, Q2, and Q3. Call them the quadrants of the triangle. And then here is the formula. That's 16 times the area squared of the triangle squared equals Q1 plus Q2 plus Q3 all squared minus twice Q1 squared plus Q2 squared plus Q3 squared. This formula is a lot more suited to actual calculations with coordinate geometry. So just to give an example, suppose we have a triangle with sides 0, 0, let's say 3, 1, and 1, 2. Okay. So a simple example. Let's look at that triangle. What are the lengths of its sides? Well, the lengths of its sides involve square roots. But the quadrances of the sides are not too hard to see, because Pythagoras' theorem says that this quadrant is equal to 3 squared plus 1 squared. So that'll be 10. And this quadrant is difference 2 and 1, so 2 squared plus 1 squared would be 5. And this one would be 1 squared plus 2, that would also be 5. It's a isosceles triangle. Okay, so anyway, then the formula would be 16 times the area squared would be equal to, well, okay, so it's 5 squared plus 5 squared plus 10 squared minus 5 plus 5 plus 10 all squared minus 2 times 5 squared plus 5 squared plus 10 squared. What's that? That's 20, so it's 20 squared is 400 minus 2 times 150 times 2 is 300. So it's 100. So the area is equal to square root of 100 over 16, which is 10 over 4, which is 5 halves. Did I do that right?
Is that a triangle?
This triangle here. Sorry?
Just like two sides of 5, 1 and 10, whatever you straight line.
No, these are quadrances. Okay, this is when I write this like this, it means that's the area. The area of that square is 5. The area of this square is 5. The area of this is 10. In terms of distances, the distances would be square root of 5, square root of 5, square root of 10. So it sort of shows the advantage in working with the quadrances instead of the square roots, because you don't have a lot of square roots. Okay, there's a lot of other things that Archimedes did. He also talked about a spiral. That's like this famous thing called the Archimedean spiral. Where as you're going around at a constant rate, and you're also going out at a constant rate. So the radius is increasing at a constant rate, and the angle is increasing at a constant rate. And he used that to solve, or to help solve some famous problems, including a problem of trisecting an angle and squaring a circle. And he had a lot of other things too, but okay, that's probably a good overview of Archimedes, one of the great minds of all time. So next time we're going to turn our attention eastwards. We'll have a look at Indian and Chinese work, ancient Indian, ancient Chinese work in the number theoretical direction. Okay, so the important contributions there also very early on. So I'll see you then.